Hello, hope you're doing well. I'm off to New Mexico. Wish I was there, but I hope your day is going well. Today our topic is special right triangles, or also known as just special triangles. So, why do we care about these? Well, they help us quickly solve for missing sides and missing angles. So if you see a triangle that has a certain ratio of sides, you'll automatically know the angles and vice versa. If you see a triangle with a particular angle, you should automatically know the ratio of the sides. Remember yesterday we learned about sine, cosine, and tangent? Well, everything we're about to learn is, I guess you could say, related to that because we're going to use the ratios of these sides to quickly know what the sine, cosine, and tangent are because we'll know the side lengths. So let's get started. There's only two. There's 30, 60, 90, and 45, 45, 90. So in your notes, I'd like you to follow along. We're going to first talk about this 30, 60, 90. And to make this example go a bit smoother, we're going to start out with an equilateral triangle, and instead of using the variable x, which I think is good practice to do. But just for the sake of simplicity, I'm going to actually start with a number I know is going to work out really nice for us. So let's say in this equilateral triangle that all the sides here are 2 in length. So we've got three sides that are all 2 in length. And then we know that the angles would all have to be 60 degrees, right? So what I'm going to do to this equilateral triangle is I'm going to go ahead and split it into two. Whoops, let me see if I can get that drawn a little bit better. And now we've got all of a sudden two right triangles, but we bisected the angle on top. So now this angle on top is 30 degrees, and this angle on top is 30 degrees. So what does that mean for us? Well, now all of a sudden we've got two 30, 60, 90 triangles because we have a 30 degree, a 60 degree, and a 90 degree angle in them. But you may remember that we split this into two, so that means that from here to here is 1, and from here to here is 1 in length. So what I'd like to do for the sake of this example is just zoom in on one of these triangles. So I started with an equilateral one, and I cut it in half. So we're going to look at just 1/2. You might be wondering right now, why am I showing you all this? It seems kind of strange. Why are you just throwing all these numbers up there? Well, I'm trying to help you see where the ratios for the 30, 60, 90 triangle come from, and eventually you're going to want to basically memorize them so you can apply them to problems. So this 30, 60, 90, let's kind of zoom in here on one of these, one of the halves. So we split that in half, right? So we know this side's still 2, and this side's 1 now because we split the bottom in half. So then what would this missing leg be, this missing leg over here? Well, we can use the Pythagorean theorem. So we know the hypotenuse is 2, and one of the legs is 1, but we're missing this other leg. Let's call it side B for now. So we know 1 squared plus b squared is supposed to equal 2 squared. So when we do the algebra on this, b squared is now going to equal 4 minus 1, or b squared is going to equal 3. So that leg must equal the square root of 3. So when I write that in, the square root of 3, now all of a sudden we have this special 30, 60, 90 triangle where the sides relate to each other in a very special way. And it's important that we mark the angles here to help us see. This is the 60 degree. This is the 30 degree angle. You're going to make sure that this part right here is in your notes. And here's why. You basically need to memorize that in a 30, 60, 90 degree triangle, the side across from the 60 degree would be square root of 3. The side across from the 90 would be 2, and the side across from the 30 would be 1. And it doesn't mean that every triangle has these side lengths. What it means is every 30, 60, 90 degree triangle will have sides that relate to each other in this same way. So what do I mean by that? Well, let me give myself just a little bit more room here. If I was to give you another triangle, and I'll make this first example a little on the easier side for us. And you were given this information. You automatically know this is a 30, 60, 90 because this has to be 60 to get us to 180. But let's say I told you that this bottom side here was 5 centimeters. Now all of a sudden, using these ratios, you can very quickly say, okay, so this must be 10 centimeters because you see this side is always twice the length of this side. 10 is twice the length of 5. And then this must be 5 square roots of 3 centimeters long. Because when this side's 1, this side's the square root of 3. So everything just got multiplied by 5. And so you can use these side ratios to extrapolate or to help you solve for those missing sides. Now, let's come back to this original triangle. These make a lot of sense because if you think about it, the side across from the smallest angle should be the smallest, and 1 is the smallest number. The side across from the largest angle should be the largest, and 2 is the largest number. And then the middle angle should have the middle number, and the square root of 3 is between 1 and 2. So the side length ratios match the ratios of the angles, so to speak. They don't match proportionally, but at least in the case of knowing that, well, actually they do. They do match, because if you want to think about it, yeah, they do, because 30 relates to 60 the same way that 1 relates to 2. And so that's one way to remember where these numbers belong, is by using the size of the angles to help you determine the sides of the triangle. So the size of the angle, or the angle measure, to determine the sides of the triangle. All right, so let's look at another problem where we would apply this. So if I know this is true, this ratio here, if I made this a little bit more difficult, so let's say we're given a triangle, and we're told that this is 30 degrees and this is 60 degrees, not drawn to scale. And we're told that this is 7. Okay, it's a little harder now to apply the, I guess you could say, the proportional reasoning to solve for the missing sides, because first we have to recognize, excuse me, that the angles aren't aligned. So the first thing I like to do in a problem like this, where I'm supposed to find these missing sides, is I like to draw my reference, or this triangle right here, in the same orientation as a triangle I was given. So 60, 30. And so I'm going to remember that the side across from the 60 is always the square root of 3. And I'm going to remember the hypotenuse is always 2, and the side across from the 30 degrees, that's always 1. So now I have to ask myself, how does this relate? Well, it looks like, again, the 7, every side was multiplied by 7. So that means that this must be 14, and this must be 7 square roots of 3. Okay, interesting. Not too bad, right? Well, what if the numbers don't work out so nicely? Let's look at one more example on how we might apply this. So in the following triangle, or in this triangle example, we're supposed to solve for x and y. But we're given only one side, but we're told it's a 30, 60, 90 degree triangle. So again, the first thing I like to do before I solve a problem like this is draw my special triangle with those ratios that I know are true. So again, across from the 60 degree angle, I know that's going to be the middle number, so the square root of 3. I know the one across from the 90, or the hypotenuse, is 2, and the side across from the 30 is 1. All right, so I was given 4, but how does that work exactly? Because you can see that it's not easy for me to figure out, how did I get from the square root of 3 to 4? What's going on here mathematically? Well, you could just build a proportion to solve this. So these are similar triangles, and that's the whole point. Because they have the same angles, they're similar. So now all of a sudden I can set up myself some proportions to solve. So I know that 4 over the square root of 3 is equal to x over 2. And I know that 4 over the square root of 3 is equal to y over 1. So 4 over the square root of 3 is equal to y over 1. And 4 over the square root of 3 is equal to x over 2. So now I've got these proportions, and I can solve for y, and I can solve for x. So you're essentially using that special triangle as a similar triangle, taking those numbers off the sides and using it to solve for the missing variables. So there is another special triangle, excuse me, 45, 45, 90. But rather than me showing you a bunch of examples, I'm just going to give you the side ratios, and I think you can go from there, because the same techniques to solve problems would apply. You can draw your reference triangle and use the side ratios to solve for missing sides. So it's the exact same concept, but because they're different angles, the sides relate to each other differently. So I'm only going to take about a minute to give you those ratios. So what are the ratios of a 45, 45, 90? Well, you might guess already that that's got to be an isosceles right triangle because two of the angles are the same. So again, if I wanted to insert numbers or even x's or variables onto the sides, it would all come out to the same ratio here because these sides must be congruent. So if I was going to use x, for example, and I wanted to solve for the hypotenuse, I know I just have to go x squared plus x squared equals, we'll make the hypotenuse c squared. So 2x squared equals c squared, or c is equal to the square root of 2x squared, which we know is x square roots of 2. So that would mean that c is x square roots of 2. And all I did there was use the Pythagorean theorem to solve for the hypotenuse. That can be a little confusing though, so let's try and use numbers. Numbers might help us out a little bit. So again, we're looking at the 45, 45, 90. So let's insert the numbers. And let's use the number 1. So this angle here is 45 and this angle up here is 45. We know these are congruent. That's a pretty ugly looking triangle. I apologize for that. So if this side was 1, this side would be 1. Well, what would the hypotenuse be? Well, 1 squared plus 1 squared equals the hypotenuse squared, or 2 equals the hypotenuse squared. So this must be the square root of 2. So that's all there is to it. Your special ratios for a 45, 45, 90 are 1, 1, square root of 2. And remember, the one for the 30, 60, 90. The one across from the 30 we know is 1. The one across from the 60 is square root of 3. And the one across from the 90 is 2. So using these special triangle ratios, you can use them as similar triangles to solve for missing sides in other 45, 45, 90, and 30, 60, 90 triangles. Best of luck to you, and thanks for taking notes and listening.